The USS Gerald R. Ford is the most expensive warship ever built. It is 1,106 feet long, displaces over 100,000 tons at full load, and is powered by 2 nuclear reactors that can drive it at more than 30 knots indefinitely without refueling. It carries approximately 80 aircraft, 5,000 personnel, and enough weapons and aviation fuel to sustain combat operations for weeks without resupply. When this ship needs to stop, not slow down, not come alongside a pier, but hold position in open water against wind, current, and the movement of the sea, it drops an anchor that weighs 30,000 pounds, attached to a chain that is 1,440 feet long, with each individual link weighing 136 pounds. The process of deploying that anchor on a ship of this size, and retrieving it when operations require the carrier to move, is not a simple mechanical procedure. It is a coordinated multi-department operation that requires specific preparation, precise timing, clear communication between the bridge and the forecastle crew, and a chain of physical checks that must be completed correctly before anyone releases the brake. This is what that process actually looks like. The anchor on a Gerald R. Ford-class carrier is a stockless design, a shank with 2 pivoting flukes at the bottom that rotate and bite into the seabed when the chain pulls them horizontally. The anchor itself does not hold the ship, the chain does. This is the principle that most people do not immediately grasp about anchoring. When the anchor settles on the bottom and the ship drifts back, the chain lays along the seafloor in a curve. The pull on the anchor from a long horizontal run of chain keeps the flukes pressed downward into the seabed. If the chain were vertical, straight up from anchor to ship, the pull would simply lift the anchor off the bottom. The length of chain deployed relative to the water depth is called the scope, and the standard ratio is between 5:1 and 7:1. In 30 meters of water, that means deploying between 150 and 210 meters of chain. For a ship operating in a typical anchorage of 30 to 50 meters depth, that ratio determines both the holding power and the swing circle, the radius within which the carrier can move as wind and current shift its heading while anchored. The chain for the Ford class runs through the hawsepipe, a tube built into the bow of the ship that guides the chain from the forecastle deck down through the hull to the opening near the waterline. The windlass, a large hydraulic-powered drum mechanism, controls the speed at which chain pays out during deployment and hauls it back in during recovery. When the anchor is set and the ship is holding, a device called the Devil's Claw or chain stopper transfers the entire load of the chain onto the ship's hull structure directly, taking all strain off the windlass so it does not bear the anchoring load continuously. The Ford-class anchor system was specifically engineered to weigh half what the Nimitz-class system weighs, a design decision that reflects the broader weight reduction program across the entire Gerald R. Ford design. Huntington Ingalls Industries, the shipyard that built the Ford at Newport News, confirmed in testing documentation published in 2014 that the new anchor and chain weigh 30,000 pounds combined, against the approximately 60,000 pounds of the Nimitz-class equivalent. Each link in the Ford's chain weighs 136 pounds compared to up to 350 pounds per link on the Nimitz. The holding power is not reduced, it is maintained through the use of higher strength steel alloy that achieves the same structural performance at lower mass. Before the Ford was delivered, HII conducted full load tests of the anchor windlass system at Newport News Shipbuilding, simulating both 180-foot and 360-foot drops under load to verify that the system performed as designed under conditions that replicate actual deployment. This kind of pre-delivery testing is standard for a system where a failure during a real anchoring evolution, a windlass that cannot hold a loaded chain, a stopper that fails under the full weight of a deployed anchor, could mean losing the entire ground tackle over the bow of a $13 billion warship. Subscribe, we build these equations every week. The bridge notifies the forecastle crew approximately 30 minutes before reaching the anchoring position. This lead time is not procedural courtesy, it is operational necessity. The forecastle team must start the windlass hydraulic system and allow it to reach operating temperature and pressure before any load is applied. Both anchors are unlashed even if only one is designated for deployment, because conditions can change during the approach and the crew must be able to use either side quickly. A complete visual inspection of the windlass chain, brakes, and stoppers is conducted before anything moves. The windlass gears are engaged and disengaged to confirm they are not seized. A seized windlass on a ship approaching an anchorage is an emergency, not an inconvenience. The bridge team simultaneously has confirmed the anchorage position. The depth, the seabed composition, sand or firm mud gives the best holding, rock gives almost none. The swing circle radius to verify the carrier will not contact other anchored vessels as wind shifts its heading, and the tidal current direction that will determine which way the chain lays once deployed. The ship reduces speed progressively. By the time the anchor is ready to deploy, the carrier is at 1 to 2 knots or effectively stopped with slight sternway. This is critical. An anchor dropped from the hawsepipe with the ship still moving forward at any meaningful speed will have the chain pile on top of it on the seafloor, and when the ship swings back, it will pull the chain across the anchor and foul it. The anchor is not simply released from the surface. It is lowered under controlled brake to a point close above the seabed before being let go. The standard guidance is no more than 20 meters of drop height, because beyond that the anchor gains enough momentum that the windlass brake cannot hold the chain and it will run to the bitter end, potentially taking the entire ground tackle over the bow. Once the anchor is on the bottom, the chain pays out under controlled brake pressure as the ship moves astern. The bosun calls the shackle count as the color-coded Kenter shackles, the larger links that mark each 27.5-meter section of chain, pass across the deck. When the designated scope is laid out, the brake is fully engaged, the devil's claw is set to transfer load to the hull, and the windlass is disengaged. The ship then backs down with its engines to drive the flukes into the seabed under power. The anchoring procedure does not end when the carrier stops moving and the chain is secure. An anchor watch is posted for the entire period the ship is anchored. The watch officer takes regular compass bearings to fixed landmarks or uses GPS position logging to confirm the ship has not moved beyond the expected swing circle, the radius within which normal weather-driven heading changes will naturally move the bow. A dragging anchor does not always announce itself loudly. The first sign is often a gradual change in GPS position, a chain that runs at an unusual angle relative to the bow, or tension that feels jerky rather than smooth, indicating the anchor is bumping across the bottom rather than holding. If conditions deteriorate, wind increases, current strengthens, the watch may need to deploy additional chain length to increase scope and improve holding power, or weigh anchor entirely and re-anchor in a more sheltered position. Recovering a fouled anchor, one where the chain has wrapped around the shank or flukes during retrieval, is among the more demanding forecastle evolutions. The standard approach is to change the direction of pull by maneuvering the ship, applying shock loads to the chain by alternately heaving and easing the windlass, or using the ship's engines in different headings to lever the anchor free from a different angle. In cases where the anchor cannot be freed mechanically, divers may be required to go over the side, a time-consuming operation that can delay a carrier's departure for hours. The ratio that defines everything about anchoring a U.S. Navy aircraft carrier is this: 1,106 feet of nuclear-powered warship, displacing over 100,000 tons, worth $13 billion, held in position by 2 steel flukes buried 3 to 5 meters into the seafloor by the weight and geometry of a chain. The principle has not changed since wooden sailing ships first used the same method in the same way. The physics of scope, of horizontal pull-setting flukes, of the catenary curve in the chain absorbing the shock of wave motion, these are the same today as they were 400 years ago. What has changed is the scale, the materials, and the procedural discipline that a modern naval anchoring operation requires. The forecastle crew who execute this evolution on a Gerald R. Ford-class carrier are working with 30,000 pounds of steel moving through a hawsepipe at a speed that the windlass brake controls one friction band at a time, on the bow of a vessel so large that the crew member standing at the windlass controls cannot see the water where the anchor enters it. The communication between bridge and forecastle, speed commands, shackle counts, scope confirmation, engine orders for backing down, is the mechanism through which a $13 billion ship and its equipment are protected from the consequences of getting any part of the sequence wrong. The anchor itself is a remarkably simple machine. The process of deploying it correctly on the world's most expensive warship is not simple at all. How the Gerald R. Ford's electromagnetic catapult system works, and why it replaced the steam catapult that served the Navy for 60 years. That full breakdown is already on this channel. This video is based on publicly available reports and analysis. Some details may be subject to change.